Before we go into the question of RISC versus CISC, let's actually look at why we use RISC, why we use CISC. So RISC is used for systems such as smartphones, tablet computers like an iPad. Why? Because all about energy efficiency. They don't take as much power to use. Now they also allow us for things like multitasking. It does give us that flexibility. The reason why it's energy efficient is because it takes up, or uses, should I say, simple instructions, which means less processing power. Less processing power, less energy being used. So energy efficient and cost is low. Tasks can be done quickly as well. So smartphones, tablets, and any system which you could argue is lightweight in itself and relies on battery life especially. We then have CISC. This is where we talk about PCs, laptops. We've got more complex software, like complex operating systems, which are being used, complex apps. CISC, guess what? Can deal with complex instructions. So we're talking about things like 3D gaming. It can do simple things as well, but the point being is it can do more than RISC in essence. So it can deal with large instruction sets, so not just complicated large instructions. So a website server, which is having to deal with thousands and thousands of people, it can deal with that really effectively. It can do it quickly. Now, if you're just doing something which is like an embedded system where it performs one task only, you're talking about RISC. Simple systems, optimized for speed. CISC is where you're going to be using computers and laptops which can do many different jobs. Some will be really complicated. CISC can deal with that complexity. You'd appreciate that when I did say that RISC is being used for phones and tablets, that tablets and phones are being made more and more advanced. So expect there to be a bit of a merge between RISC and CISC in real life. So let's get on with the question itself. Okay, pause the video, give this question a go yourself first. Right, so let's rock and roll. This is quite easy because it's kind of building on the previous question. RISC, I'm just going to do R for RISC and C for CISC. So RISC has fewer instructions, and then I need to put about CISC, and CISC has more instructions. Which is basically saying RISC's architecture is designed, so let me just put an arrow under RISC. Limited architecture in terms of its design. It's all about simple processing. More complex architecture. I do arc. So that is one difference to begin with. The next difference, RISC has many registers, whilst CISC has fewer registers. This allows more data to be processed, within the CPU. Reducing need for RAM access, while CISC relies more memory access. So it tries to perform its calculations without having to store it within, well, try to basically, let me rephrase that. RISC, when it processes instructions, tries to not use RAM as much as possible. So it stores things within the CPU registers itself. CISC doesn't have as many registers, so it uses RAM more in terms of its calculations. We then have RISC's instructions are simple and CISC's instructions are complex. We talked about this before. I'm not going to go into that again. It's more about RISC being efficient and quick to perform calculations. CISC, on the other hand, can do more complex tasks, but requires more cycles sometimes to complete. RISC, fewer instruction formats, and CISC, many instruction formats, which means simple to debug or decode. This is needed for its more complex tasks. RISC, single cycle instructions, whilst CISC uses multi-cycle instructions. RISC, because the same length, easier to fetch and decode, vary in length, didn't mean to do that, which means basically when it varies in length, you're going to have a situation where you can have more compact representations. We then have RISC, better at pipelining, and CISC, poorer. This is due to simple instructions where instructions can be overlapped. Whereas with CISC, because they're variables in terms of the instruction size, you're dealing with a variability. What that basically is going to mean, it's harder to predict and do the pipelining and the overlapping. We then are going to talk about RISC, less complex circuits, whereas with CISC, more complex design. What does that mean? Well, this is more cost effective and power efficient. We talked about that in a previous question. CISC, on the other hand, needs complex circuitry to decode, so it'll cost more. We then have RISC has fewer addressing modes, while CISC has more. That is because RISC simplifies memory access. It limits the ways we can access memory. CISC, on the other hand, has a wide range, greater flexibility, because it has to deal with a wider range of different tasks. Flexibility. What is this ruler? Go away. We then have RISC, uses RAM more, which kind of contradicts what I said earlier, but it is slightly different points. CISC uses cache. Well, in terms of loading and storing, RISC uses RAM more. Even though it has more registers, few registers. Let me say that again. RISC has more registers than CISC, but it still uses RAM when it comes to loading and storing. CISC wants to speed up the process, so it uses cache memory, so it can deal with the complexity of the instructions. So it means quick access to data and the instructions without having to go all the way to RAM. RISC, hardwired control unit, and CISC, programmable. This is ideal for speed because it's been programmed to deal with efficiently what it needs to deal with. CISC, on the other hand, we can customize to the tasks, the instruction sets we're going to be using, etc. But it could be slower. This has got one job only. It does it well. Finally, RISC uses load and store instructions to address memory. Whilst CISC has many types, as well as load and store, which means it can deal with, again, complex instructions. So let's go through this table. Pause the video, give it a go yourself first. Alright, we know what uses a small instruction set, RISC. We know what's done in a single instruction, and it also has limited addressing modes, RISC. What uses fewer registers, CISC. What uses both hardwired and microcoded, that means it can be programmable, CISC. Now, this next one, I did mention for CISC, it uses a cache more, but I'm now going to talk to you very quickly about what this means, split between the data and instructions, which is RISC, by the way. Okay, so RISC, what it does in its cache is it separates, so you've got instructions in one room and data in another. So if I was giving a very quick analogy, imagine it's like a kitchen and you've got different pantries. This is, oops, what did I just do to instructions? Okay, so this is for the recipes, and this is for the ingredients. So the data is the ingredients, the recipes are the instructions. Now, this allows us to have parallel access for RISC, where we've got a chef which can be going into this pantry to deal with the recipes, and a chef which is responsible for grabbing any ingredients. This can be done at the same time, so there's no waiting time. As these pantries have different purposes, I mean, let's imagine that the ingredient pantry might have frequently used items at the front, so we can have our ingredients in order. At the back, we've got things which we never use. At the front, this is a door, by the way, we've got our most frequently ones which are used. It allows us to find things really, really quickly. Since our chefs don't have to wait for each other, we can get on with things without, so the ingredient guy can get on with things without really having a recipe, which means there's no bottleneck. With them kept separately, there's no danger of them basically getting ingredients and recipes mixed up with each other. CISC, on the other hand, works slightly differently. So with CISC, we have one room only. In that room, we've got the instructions and the data together in CISC, or recipes and the ingredients. This will mean that we've got one chef. The chef may need to search for all the different recipes, or they may need to search for, or shall we say, and search through the different ingredients. This could slow down meal prep. If you have a situation where you've got multiple chefs working together, so you have a chef going into recipes and one going into the ingredients, it will lead to, remember, it's in the same room. If it's in the same room, only one of them actually will be able to enter this room at a time. So we have to wait until one of them's done. So if this guy wants to go to the recipes, this guy is going to the ingredients. We have to wait for this guy to leave for this guy to go in. Whereas in this situation where we're splitting the data and the instructions, it allows multiple parallel. This basically means that efficiency levels for CISC using this style of cache isn't going to be very, very at the highest level. It really depends upon how organized our cache is. If our cache is really organized, we can still run quickly, but any type of disorganization in our cache will lead to delays. However, managing one pantry is simple, but it does require ingredients. So ingredients like organization. Managing two is slightly more challenging, which is ironic considering we keep saying RISC is more simpler than CISC. However, point made. RISC uses a system where the cache is actually split between data instructions, while CISC groups it all together. Okie dokie, so pause the video, give this question a go yourself first. Okay, which one has simplified instructions? We know it's going to be RISC. Which one emphasizes on hardware rather than the software? Well, that is going to be CISC in itself. Which one makes use of general purpose registers? That is RISC. Which one has multiple formats for instructions? CISC. Pause the video, give this question a go yourself first. Okay, so what is meant by pipelining? There are many different answers we can say for this. Processing a number of different instructions. You can say simultaneously, concurrently, at the same time. So that'll give you 1 mark. You could also talk that it is instruction. So we take instruction, level parallelism, which is simply saying that it takes multiple instructions, and just do I for multiple instructions, and as we said already, simultaneously at different stages. So running out of space of their execution execute to allow parallel processing. Sorry, my spelling, remember I am dyslexic. My bad. We can also say that to get another mark, so that would be 1 mark by the way, an instruction split into number of stages for execution. you could also build on that by saying when first stage for instruction, I'm going to do I for instruction, is completed. Do you see how specific I'm being with this? I'm talking about first stage. The next instruction can begin execution. So any of those will get you the points. Pause the video, give this question a go yourself first. This is very easy. So we've got two instructions, D followed by E, so we obviously need to put D here. Then it moves along, so it's going to be then DE, then it moves along again, DE, then it moves along, DE, then it moves along, D. Oh, I think I made a boo-boo. One sec. DE. And there you go. Pause the video, give this question a go. Okay, another easy pipelining question with a twist at the end. So we've got A, B, C, we then have A, B, C, we then have A, B, C, we then have A, B, C, and then we've got A, B, C. You'll notice though, the stages on this one are more than the last one. So we're doing fetch, decode, execute, we're accessing an operand in memory, like for calculation, and then we're writing the result to a register. So it's got more steps. The computer table shows how pipelining allows instructions to be carried out more rapidly. Each time interval represents one clock cycle. Calculate how many clock cycles are saved by the use of pipelining in the example above. And I completely messed up that last row again. I'm an idiot. A, B, C. Let's try that again. Okay, so we know that it takes one clock cycle for the first instruction to be, 7 time intervals, or should we say 7 cycles, with pipelining being used. So C was our last one. For C to get to the end, we're at number 7. So what I'm going to do is I'm going to write 7 down here. And that's going to be with pipelining. If we didn't have pipelining, we would have to do all of A, then B, then star and C. So how can we calculate that? Well, we've got 5 stages. So I'm going to write 5 here. We've got 3 different instructions. So I'm going to times that by 3. This will give us 15. So without pipelining, the time interval would be on 15 all the way down here. If we're going to do A. Once A is finished, we then begin B, 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 B. When B is finished, C, 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 which will be 15. Yeah, I put 15 a little bit too far. So to work out how much we're saving by the use of pipelining, it's just going to be 15 minus 7 equals 8 saved. You know the deal, pause the video, give this question a go yourself first. Okay, so why does it fail pipelining when we're doing this? What I'm going to do is I'm going to give these numbers. So we've got op1, 4, we've got op2, 2, and we've got a destination where it needs to go. So if we did, actually I may as well do the 4 and 2 down here. R1's being 4, R2 is 2, so 4 plus 2, if we add them together. And we're going to put it into R3. So R3 should have the number 6 in it. But here's the thing. Because we're doing pipelining, we are now using R3 in this calculation here. So it should be 6 plus whatever number we've got here, like 10, and it should give us 16. The issue is we do forward to here, but because we're doing pipelining, we're using R3 in the next sum, but we're not ready to use it in the next sum because we haven't yet put it into, we haven't performed our add to put it into here. So the result of R1 plus R2 is not yet stored in R3 before the next instruction kicks in, starts. I'm going to put where it needs to load the value from R3. That should say 3. Because of this, we call this a data dependency issue, where R3 is fetched on same clock pulse. The instructions were produced by a compiler after translation of a high-level program language. The compiler is not capable of code optimization. State how the code from the compiler could have been optimized to overcome the problem in this situation. Well, this is bringing in another topic where we looked at the role of compilers and optimization. If we were to optimize this, what we can do is recognize that instruction 1, instruction 2, instruction 3. Instruction 3 isn't dependent on any of the other instructions, so we can actually make that run first. So by running instruction 3 first, it will then lead to this order of 1, 2, 3. By the time we get to putting the result of this and this into this, it would be done. So we can then use it on this line if you put it into a pipelining little table. Pause the video, give these 2 questions to go yourself first. Okay, first one I'm not going to go into, I'm just going to show you on mark scheme for it. Multi-level parallelism, blah 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 blah, you can say as well from last time. Okay, so in this next question we've got processing instructions is split into 5 stages. Great. Each stage is carried out at different register, pipelining 6 instructions. So you can do it as numbers or you can do it as letters. I'm going to do it as letters, so we're going to have A, B, C, D, E, F. Then we're going to have A, B, C, D, E, F, A, B, C, D, E, F, A, B, C, D, E, F, and then A, B, C, D, E, F. Done. Okay, let's look at computer architecture now. Let's pause the video, give it a go yourself first. Okay, so most parallel computer systems use this type of architecture. Well, it's obviously going to be MIMD. Used for video games, for 3D graphics. Well, that'll be SIMD. To control a washing machine, SISD. And the number of processing units. Each processing unit executes the same instruction, but on different data. Again, that would be SIMD. Nice and easy start. Okay, pause the video, give this question a go. Alright, so the first one is each processor executes a different instruction. Well, that would be MIMD. It can deal with many things at the same time. That's what the architecture is for. It executes different instructions on different pieces of data. So it's used for like supercomputers, parallel computers. There's only one processor. Well, that would be SISD. It's a traditional single core processor, old school. Each processor executes the same instruction input but using data available in the dedicated memory. That will be SIMD. So it's great for like parallel tasks, not parallel processing, parallel tasks like graphics rendering. So when it's displaying a game on the screen, and it's responsible for putting the pixels in place, different color pixels, the instruction will be the same. Put in the color, put in the color, put in the color, but the colors will be different for each pixel. Each processor typically has its own partition within a shared memory. Well, that will be MIMD because they work independently from each other. They work on their own thing. Independent parallel tasks. So there are 4 different architectures which are used in parallel processing. So we call it Flynn's taxonomy. You've got SISD, SIMD, MIMD, and that's it, say D, and MISD. So pause the video, give this question a go yourself first. Alright, so SISD. One processor which can execute one set of instructions on one set of data. So we're dealing with such as a traditional von Neumann, so fetch, decode, execute, which you've learned before, core like i3, so it's a single i3 single core processor on all computers. You've then got SIMD, which is ALUs several. Each ALU executes same set of instructions on several sets of data. So that would be, again, the GPU. Graphics processing is a great one. One instruction, put all the pixels in place, the data, millions of different colors. MISD, let's just do that down here, which is going to be several processors. Each processor executes different sets of instructions on one set, let me just move down, of data. Several processors, each processor executes different sets of instructions on the same set of data. So where is this used? Well, space shuttle flight for critical control systems. So you have the same instruction, the same set of instructions on the same input data multiple times, just to make sure, is it working? Check. Is it working? Check. Is it working? Check. Then you've got MIMD, which is again several people processors. But each processor executes different instructions on different sets of data.